Good afternoon. Welcome to today's introduction to COMSOL modules webinar on microelectromechanical systems module, MEMS module. This is Hakim Al Aswawi, technical support engineer at Al Engineering and Agencies. We are the sole distributor of COMSOL multiphysics in the Arab countries. Continuing our series to introduce COMSOL modules, today we're going to talk about the MEMS module. We're going to discuss what is MEMS, what is included in the microelectromechanical systems, general tools that we have in COMSOL multiphysics that can facilitate modeling MEMS, and the interface for the MEMS module and what we can find as features in COMSOL. After that, we're going to do a simple example on piezoelectric materials, piezoelectric tube, and then we can conclude it with the question and answer session. The microelectromechanical system, from the name, as you can see, it includes the multiphysics of between electrical, structural, microfluidics, and thermal physics in this part. So we are combining all of these into one module or into one model. So it's inherently a multiphysics problem. So we cannot solve MEMS module without actually having multiphysics, since it involves all of these four parts or even more. So some of the applications you can find under the MEMS module are the MEMS devices. You can model accelerometers, pressure sensors, micromirrors, micromotors, RF switches, tunable filters, antennas, and under microfluidics or the biomems, you can model the microfluidic machines like micropumps and microvalves, electrokinetic flows. Also, you can use it to model gyroscopes, so SAW or BW resonators, so bow resonators. Some of the challenges that we have when simulating MEMS structures or microelectromechanical systems is the different forces dominating at different lengths of scales. So also the aspect ratio might be very far apart. So something that can be very thin or very narrow, can also have with respect to these dimensions, a very wide or a very long dimension. So the high aspect ratio between the length, width, or thickness might be a problem in simulating or creating them as a model. The multiphysics and multi-materials used in these models can vary widely from non-linear, anisotropic, and other properties that are available in the system. So that might complicate it even more. And also the physics, combining all electrical, mechanical, structural, and thermal physics or equations in the same model can make it a very complex model. Based on that, in COMSOL, we have multiple tools that can facilitate modeling the MEMS structures on MEMS models. We have geometrical tools that can help us either by drawing shells, or certain tools that can help us draw shells or define shells, thin structures, high aspect ratio structures, high aspect ratio geometrical entities. You can use also the material library. You can find the parts library, which is available. You can find certain types of objects there. You can also use the material database, where you can find many materials like certain polymers, semiconductors, and also different types of alloys and piezoelectric materials included. Or you can edit it to the user-defined material. You can use and also user-defined coordinate system like we're going to use today. So you can change the coordinate system between the default one and different other coordinate systems. As I've said earlier, you can model thin layers such as membranes and shells, which is included in the physics. You don't have to actually draw a thin element and mesh it, which is going to consume lots of memory and resources in your computer. You can just simulate it as a thin layer, as a boundary condition or domain condition. You can also use the PML, perfectly matched layer, to model certain types of models, which assumes a certain type of domain or based on a certain equation that can assist you or facilitate your model. And then at the end, you can change your model or convert it to an application, either by using the COMSOL server and sharing it with your colleagues or students, or use the COMSOL compiler, which helps you or assists you in packaging this model into a standalone application or app that can run on any computer without the need of COMSOL license or a COMSOL installation or anybody needing to know how to use COMSOL to use this app later. In the geometrical tools, you can find in the parts library some parameterized objects. You can use work planes to extrude certain types of geometries. For example, if I have a very thin element like this rectangle or these rods, I can just draw it as a plane on a work plane and then extrude to a certain height. I can extrude different bits and pieces to certain different heights. I can use copy, array, or move or replicate the objects multiple times. So I don't have to draw, for example, this rod one time, multiple times. I can just draw it one time and use the array to duplicate it X number of times in certain direction or a certain axis. So I don't have to create it one by one. I can also import it from different other softwares. For example, using the ECAD file format or CAD import tools or other live links we have in COMSOL. We can also use the material database, as I said earlier. We have multiple piezoelectric materials and metal semiconductors and insulators and polymers, which can be used in the MEMS structures or MEMS devices, which you can find under the library. We can also have different types of material properties. So I have anisotropic, nonlinear, inhomogeneous. So all of these can assist us creating different materials with different behaviors under certain conditions or certain applied parameters or forces, for example. These can create complex or more realistic models, which can simulate the real device without actually needing to prototype it, since these devices are like very hard to create in real life. You're just wasting money if you're just trying to prototype it one time after another without having the accurate or the set upon dimensions and properties at the end. We also use different type of boundary conditions to model thin layers. For example, in this micro heater, you can use the shell property. You can also use the PML, which we discussed earlier in the MEMS module, like micro antennas. That's an example, or resonators. The physics interface or the interfaces that are available which would be available in the MEMS module, you will not have a single tree that's called MEMS or micro electromechanical systems. You will have it distributed upon the other trees. So as soon as you acquire the MEMS module, you will find part of it under the AC/DC module, the other part under fluid flow, which is, for example, fluid structure interaction, the other part under heat transfer and structure mechanics. These are all the features that can be found in the MEMS module. You can find even more specification about what exactly is included in this module under the specification chart on the comsolwebsite.com. You can go to comsol.com and on the bottom you can find the specification chart and you can see exactly what is included in this module, even the types of studies, type of geometries, everything. So this is to conclude our description of the module itself. As for the example, what we're going to do is the piezoceramic or piezoelectric tube. It's composed of a piezoceramic material. The whole idea is that when you apply certain potential difference on this tube, the dimensions of the tube constricts or expands. It depends upon the kind of voltage or what is the direction of the potential difference. And the dimension of the tube changes and certain stresses develop in the tube. On the other hand, because it's a piezoelectric material, if you apply a certain pressure of certain stresses upon the tube, a potential difference is going to be created between two poles of the tube. We can do this in model. Both models can be created from the same exact model. We're going to see how we can go back and forth between these two models without actually creating two separate or two distinctive models. Since this is just a hollow tube, so instead of having it in 3D, we can have a 2D axisymmetric model. So the whole idea is having a slice which is symmetrical around an axis. In our case, if you assume that we have an axis in the middle, like here, so our symmetrical element is going to be a floating rectangle a little bit far away from the center of the axis, which is this rectangle. The dimensions of this rectangle is going to be 240 micrometer in width, 620 micrometer in height, and the position is going to be off center 380 micrometers. And this is the material, which is lead zirconium titanium. Let me start by opening console on my side. We will start with the model wizard, as I've said, 2D axisymmetric. We will select the piezoelectrical material, so you can go structure mechanics, piezoelectricity. By using this multi-physics node, it's going to include all the needed nodes. For example, electrical current, electrostatics, sorry, and structure mechanics, which is solid mechanics, and the multi-physics combining them together. Next, I will select my study, which is a stationary study, and click Done. So this is to start with this model, just a blank space with axis of symmetry in the middle. I'm going to start with my geometry to create my dimensions and insert my dimensions to create my rectangle. So click on rectangle. Before that, I will just need to change the length unit to micrometers to just save time by not typing in every time micrometer, micrometer, micrometer. So yeah, by default, this is the micrometer unit. We said that the width is 240 and the height is 620. So width is 240 and the height is 620. And the position in the other direction is 380. So this should be my rectangle. It's off center. As you can see, this is the axis of rotation. It's off center in the R direction, which is outside. So that's it. As for the material, we said we're going to select the PZT. So add material. You can go to MEMS, semiconductor. I'm not sure where is exactly the material, so let's search for it. So PZT. Yeah, it's in the built-in, so it's available in comps. So since I have only one domain by default, it's going to be assigned to this material. Next, I can go to solid mechanics. In my solid mechanics, I'm going to start the model by applying a potential difference and see how it deforms, how it changes. So for me to do that, I need to fix it to a certain reference plane and apply a certain coordinate system on it. So I can go to piezoelectric material first, go to my coordinate system, ZX system, which will make my z-axis in the r direction and my x-axis in this z direction. Next, I can go to solid mechanics, apply a roller boundary on this part. So the roller boundary provides you an anchor point for this plane, but instead of just gluing it or fixing it to the plane, in our case, this plane, it can move around but not detach from this plane. So it can float around left and right, but cannot go in the z direction or in the up direction. So if it expands, it can go left, or it contracts, it can go to the right or left, but it cannot move up and down on this plane. This is in contrary to the fixed constraint. The fixed constraint is just you're anchoring this plane to this side or this boundary, which can prevent any deformation. It cannot shrink, it cannot expand, it cannot move to in any way up, down, left, or right. So it will create a different kind of effect fixing it to this plane. So roller is our best choice in this case. As for the electrostatics, I can apply the electrical current, or in our case, a certain type of voltage. So if I go to my electrostatics, physics, boundary condition. I can go to ground, and this would be my ground. And then I can apply terminal on this side and voltage, for example, 0.1 volt. Next, under mesh, I can use the map mesh and then create a map mesh. Yeah, since it's a very symmetrical model and symmetrical object, I can use the map mesh to split a rectangle to a smaller squares or rectangles. I can then compute it this way. It should work pretty fast, so let me check if it's done. So yeah, it's done. So as you can see, certain stresses and deformation happen to the tube when we apply the electrical current between this side and that side, which is the ground. So if we wanted to create two models in one model, instead of having to recreate the model again and applying a certain type of pressure from, for example, in the inside walls and see how kind of current develops or what kind of potential difference develops in the material or in the structure, we can manipulate the study options by including all our inputs for both models into the physics, and then manipulate the study to exclude certain types of inputs, as we can see now. So I can apply a certain kind of load, boundary load, so like that, from the inside part of the tube, which is this way, and apply it as pressure. And my pressure is going to be 0.1 megapascal. Yeah, uppercase instead of lowercase. So 0.1 megapascal, keeping everything as is. So now if I run it, I'm going to have an inside applied pressure from the inside wall. I'm going to have the rudder condition here. I'm going to also have the electrical current or the voltage applied from the inside part. So instead of having something like that, I can exclude in one study the boundary load, and in the other study, I can include the boundary load but exclude the potential difference, as we can see now. So I can go to the study. Under step 1, I can check the modify model configuration for study step and exclude the boundary load by clicking on disable. So for the first study, what's going to happen? I'm just applying the potential difference and disabling the load. I can create another study, which is what we did earlier. My next study is going to be the exact same thing, but switching around. Double click. And then click on modify again and disable my voltage source, which is the terminal. And that's it. And if I run this one, I'm going to have a different result since I only have the pressure or the applied pressure from the inside, which will generate the potential difference across the material or across the device without having the other study interfering. So if I go to my next study, I can see that there is a generated potential difference because of the applied pressure from this side. It's a bit different, but yeah. Applied 0.1 megapascal from one side, and then I generated the pressure here. So if I look at the revolved geometry, since this is an axisymmetric model, it can generate a revolved model. So this is my 3D model. I can also manipulate my 3D model by going to dataset under revolve, revolution. Yes, I can manipulate the revolution. Instead of having a 360, I can say, for example, 210 for study one. So just a bit, I can see the cross section here. So if I I can go again to the potential difference revolve. Yes. So I can see the inside part of the model. I can create whatever plot I would like from these. This is just raw data. I can create whatever plot I want from these elements.